You probably bumped many times into this amazing artsy maps of a relative elevation model using Lidar data, but you probably didn't know how to make them yourself. Well, you come to the right place, because in today's tutorial, I will show you from the beginning how you can get this Lidar data, how you can create relative elevation model, and then how you can create some really powerful 2D and 3D maps. All right, so our first step is to install and then load the packages that we need. In this tutorial, we'll be using Terrain R package for fetching Lidar data. So to install that package, the best way to go about it is to install it from the GitHub repo. So for that purpose, we'll be using the DevTools package. And unless you already have it, you should definitely install it here. And once you install it, you can fetch from DevTools a function which is called install GitHub. And then over here, you just need to pass this a link to this repo. And for installing and loading the remaining packages, Pacman will come to rescue. If you don't have package Pacman installed, you can use again this install packages to do that. I already have it here, so I can just directly use this function, which is called pload, which is going to install and then load the remaining libraries that we need. So the first library that we will load, which we already installed in the previous step, is Terrain R. This one is going to help us fetch the Lidar tiles that are necessary for our area of interest. So that's the first one. Because we will be working with raster files, we definitely need here also the Terra library. Along with Terra, we'll be also working with polygons, specifically the river lines. So we'll need the SF package, which is going to help us deal with the simple features. And while we're talking about river lines, we will fetch this data using the OSM data package. So we'll be getting the river data directly from OpenStreetMaps data. Now, in this process, we will also need to kind of calculate where the digital elevation model breaks for us. And I really like to use ClassIn package, which is going to help us get the natural intervals here. And then finally, we will be, of course, visualizing this relative elevation model. And for that, we can use ggplot2. And apart from ggplot2, we will also be turning, apart from the 2D map, also into a 3D map. And for that, we can use a rayshader package. In case you're wondering what package and dependency versions I'm using, I just printed them out here for reproducibility purposes. In today's tutorial, we'll be, first of all, fetching high-resolution digital elevation model data from the US Geological Survey, and from their website, where you can actually get high-resolution data for different areas. We'll be doing that for the extent of the Snake River in Wyoming. And here is how you can do that. Our first step is to head to the browser, search for 3D Lidar Explorer, and then select the USGS Lidar Explorer map among the results. This is going to take us to this interactive map, where we should choose the DEM tab. And then click on Show Where Lidar is Available. This is going to paint the map in red for those areas that have 1 meter Lidar. We zoom in into Wyoming and look for the extent of the Snake River, for which we're going to be creating the relative elevation model in today's tutorial. Unfortunately, the USGS interface does not allow us to select our area of interest on the spot and define the bounding box coordinates. So we instead head to bboxfinder.com, and over there we zoom into our area of interest, which is this extent of the Snake River. And then on the side, we click and drag the rectangle feature, and this allows us to select our bounding box of interest. And then we simply, in the lower left corner of the screen, we fetch the bounding box coordinates and take this back to R with us. All right, so now I'm back in R. I just pasted here these bounding box coordinates. And what I'm going to do next is assign this to specific objects and then create a bounding box polygon as a simple features object. So first thing is that we'll define this as the minimum of longitude, so x min, then followed by the minimum latitude, y min. And then after that, we can also define maximum longitude. So this would be this value. And finally, maximum latitude, or y max, and this would be this last value over here. Okay, now that we have these 4 coordinates, we can go ahead and create this polygon as a simple features object. So I'm just going to simply call it BB, or bounding box. Then I'm going to use SF package, and from SF package, I'm going to use this function stsfc. And then within that one, I'm going to pass st polygon right like this. And over here, I actually need to merge together the list of these different elements in a column-wise fashion. So the first actually part of this is putting together these longitudinal values. So we're going to start with xmin, then we're going to add xmax here, then again xmax, xmin, and then finally we're going to finish off with the xmin value. So the same way we did this for the these longitude values, we're also going to do for the latitude values, but in a bit different order. So first of all, we're going to do this latitude minimum value, then follow again by latitude minimum value, then ymax or latitude maximum value, another latitude maximum value, and then finally ending here with the minimum latitude value. Now this is not everything, because over here we also need to define the coordinates reference system for this one. So if you remember from that previous window in our Explorer, the coordinates reference system is simply the WGS 84 with 4326 datum. Now that we have this extent, we can just go ahead, pass it to terrain R get tiles function, and then get downloaded locally for our purposes. It's that easy. So I'm going to call this object DEM, and then I'm going to call terrain R, and within terrain R, as I mentioned before, I'm going to be using here get tiles. So there is a small typo here, so terrain R with double R. Now within get tiles, we need to first of all define this data argument. So the data is essentially what is your bounding box, what is the area of interest for you, which we already defined. So this needs to be a simple features object. Now the second one is what is going to be the output prefix. So this is, I think, important if you have more tiles. Essentially, if this returns more tiles, you can, for example, use this one, REM, because we are building here a relative elevation model. Now we're going to make sure that this query returns only a single file of the entire area of interest for us. And I'm going to be doing that by increasing this side length here. Side length usually is set to null, but I'm actually going to increase it to 8,000 here, and this is going to make sure that I don't get like a bunch of small tiles, but I get one large tile. And then finally, or penultimate step here, is to define what is going to be a resolution. So we want to have Lidar data, and I'm going to set here that I want a resolution of 1 meter. So this is what it means. And then among these services, as we saw before, we are actually interested in the digital elevation model data. So to get that one, you just need to specify here that among the services you're looking for the elevation. And then last but not least, you can also here turn on this mode where it's going to give you information what exactly are the tiles that are being downloaded and when they are going to get downloaded. Now after running this codes, you will see that over here I issued 2 API call attempts, and within a minute's time I managed to get this raster file, and I also inspected it here. You can see that the object that is returned here, this DEM, has this elevation element and also has this name with this prefix that we defined, REM, and then with also this default, this generic name as well. So this raster file actually ended up on our local drive, but we can now directly call it within this session, simply using this DEM and then calling this elevation element within it. All right, so to call this newly downloaded raster file, what we can do is the following. For example, use Terra Rust, and then what we can pass here is this DM elevation. Of course, this assumes that you are actually working from the working directory to which you downloaded that raster file. If you, however, started a new R session, but you already have that raster file downloaded and you're working from that working directory, you can also write this. So you can again call this Terra Rust, but instead of having this element here, which is not present anymore, you can simply pass the name of your file. And in our case, this will be the name of that file together with this diff extension. And then if you quickly inspect this raster file that you just loaded, you will see that the resolution is indeed 1 meter. And you will also see here the extent for which we took it and also the name, as well as the dimension. As you can see, dimensions are quite big for such a small extent, exactly because our resolution is very, very high. All right, in this section, we'll be getting that portion of the Snake River as a simple features object, and then we'll be using that one to extract the points of this one and then make predictions about the elevation model for each of these points. So down the road, this is going to be a very important part. Now, for that, we can actually utilize the open or OSM actually data package. And then what we can do is, using this argument over here, we can pass as our bounding box that BB object that we previously defined. Now, after that, we can then again call another function from the OSM data, which is called add OSM feature. And then within this one, we need rivers. So to fetch rivers from the OpenStreetMap data, you need to specify for the key waterways, or actually a waterway. And then within the value here, you need to specify that you are specifically looking for not any waterway, but you're looking for a river. And then the last step over here is to call the third and the final function from the OSM data, which is called OSM data SF. And this one is actually going to coerce this object into a simple features or SF object. Okay, so this OSM data object returns different types of objects. So points, polygons, lines, polylines. What we need from this specific river object here is we need lines. So I'm going to actually create a new object, river SF. And then from this river object that we just got, I'm going to take OSM lines because rivers are represented by lines. All right, and after that, what I'm going to do is I'm going to make sure that the river lines we got are going to be only for the bounding box. So I'm going to go and from SF package use then NST intersection, and I'm going to then intersect this one with this object, with this bounding box or object PP. All right, and then once this is done, I actually want to union all of those line segments that I have. And the reason for that being is I want to actually then cast them into specific line strings. So I don't want to have a single multi-line string. I want to have different line strings here because I want to get as many as possible values for different segments instead of having just like several values or maybe just one value. So what I'm going to do here, I'm going to pass this to a line string object. So I want to have way more segments of this line or multiple segments, and for them down the road I will be actually predicting what is the elevation exactly for those different line segments. And the last point here is that you want to make sure that this is then turned into an SF object, and that's why I'm using here ST as SF. And then as you do this, you can then go ahead and plot these two objects, so the river plus this high resolution digital elevation model, and see what you actually have. And we can do that easily. So we can do some very quick and dirty plots, and plot here, for example, first of all this one, and then after that we can plot the geometries of our river SF object, and we can also give it here maybe a different color. So for example, for the color we can use something that is a bit visible, let's say for example gold. And we can also put here that we want to add, of course, this plot after we plot this raster file. And then you can go ahead and actually inspect by making a quick and dirty plot over here. So we can, for example, start off by adding here this dem rust file, and then followed by simply plotting here this river file, but we need to plot the geometries of this river file just like this. And to make sure just that we can clearly see the rivers, what we can do is we can also change here the color. For example, we can go for white, and very importantly we also want to add this river plot to this raster plot. All right, so this is what you should be seeing. You should be seeing this digital elevation model using this palette, and then also you should be able to see the Snake River over here, and that does not go over the board, so it stays within the bounding box of this raster area. All right, so here comes a very important part where we actually are starting to prepare for creating our relative elevation model. And the first thing we want to do here is decrease a bit the resolution of that raster file, because you remember we are here using it at 1 meter. So what we can do here is maybe scale it down a bit, or actually scale it up. So we want to actually decrease the resolution. So we can use for that Terra aggregate. You don't need to use this if you're ready to wait maybe for a few minutes. But why would you actually do that when you can simply maybe disaggregate a bit? So we can actually use here the factor of, let's say, 5. So we're going to be decreasing the resolution 5 times here. So just kind of to make our further analysis much faster. So once we do that, what we need to do next is we need to extract these digital elevation model values for each of the segments of our river plots, using, of course, this raster file with this lower resolution. So over here, we can do is we can create this object river elab, and then we can use for that purpose Terra extract. So Terra extract is going to help us extract those values. So for the X, then what we need to do is we need to provide here this aggregated raster file. So that's the first thing. And then for the Y argument, we're going to provide in here river SF. Now, this might not work with Terra because we are passing directly the SF package, or sorry, the SF object. What actually is much safer is if we coerce this one into a Terra-friendly format, and that would be this vector format. This is not all. So the next thing we want to do is we want to actually transform then this resulting data frame into a data frame with columns that have X and Y values. So for each of those segments, we will have X and Y values. And then we also want to here remove any missing values. So we don't want to deal with that. All right. And if this does not really happen, then we can also go ahead and use, for example, here na.omit, because in some cases it can happen that this is not going to completely remove those. So then when you actually inspect the first few rows of this data frame, you will notice that we have the specific digital elevation model values for each of these points denoted by X and Y. Okay, you also notice that there is a weird name for the this elevation values, elevation column, which was simply inherited from the name of the file that we previously downloaded. So what we can do is, using this object over here, we can actually rename that specific column. So we can do it like this. We can use names over here. And then we need to change the second name, so the second column. And I'm just going to use here something like elevation. I'm going to avoid using DEM because we already had an object which is called under the same name. So I'm just going to use here elevation. And one more thing. So if you, for example, run this command here, which is nrow, and then pass this river elab, this is going to give you actually the number of actually these specific segments. So over here we have over 2,000. We have this many because we also, if you remember, decreased the resolution of our raster file. If we kept the old one, we will probably have, thousands and thousands and more of these values. But this is something very important to keep in mind. Okay, so once this is done, the next step is to actually define our interpolation model, which we will then be passing to Terra and using this then to predict the values for this specific river segment. In this part, we can use inverse distance weighting for interpolation for the selected segments or the points that we have here. And for that, we can use the gstat package, which has a function which is also called gstat. So I'm actually going to create here a new model. So I'm going to call it IDW model. And then within this gstats, I'm going to first of all define a formula, and it's going to be a very naive formula. So basically, we want to predict elevation, and we're just going to here use an intercept. And we need to actually define the locations from our data frame for that purpose. And the locations are denoted, of course, by X and Y. So we need to write here that the locations are actually x and y, x plus y. And then we also need to here define what is our data. So the data is that one that we previously created, so this river Elef. And once we have this, we can also define how many of these, how many of the points we want to use for prediction. So we can use the maximum number of those points, so which is over 2000, and we just need to pass here that we want to be using the maximum number of rows from this river Elef object. Okay, so we have extracted values, we have defined our model, and now we can finally extrapolate these values based on this IDW model using Terra function, which is called interpolate. So I'm going to call this one river surface because that's exactly what we're calculating here. We're calculating river surface using interpolate from Terra. Now over here, what we need to provide are basically three arguments. The first one is what is exactly that we're going to be using here for this interpolation. So that's the first argument. Second one, what is the underlying model for prediction? And the final one, what is going to be the coordinates reference system? So what we're going to do here is simply the coordinates reference system of our DEM-RAST, or it can be also DEM-RAST aggregated. It doesn't matter. It's simply the same object in terms of the coordinates reference system. This interpolation was superbly fast, so it was done within like 5 seconds. And if it was done also on your side in a proper way, you should be able to see these two messages that the inverse distance weighted interpolation was actually calculated. And then as a final conclusive step, we can calculate the relative elevation model. Relative elevation model, or REM, is nothing else than this digital elevation model, and from it subtracting simply the river surface. That's basically it. Now, we don't want this REM to stay at this resolution, so we want to actually scale it back to that higher resolution, and we can easily do that. So I'm going to simply create then here a new object. We can use from Terra resample once more, and over here what we are going to pass is for this REM, we actually want to resample it back to this original DEM-RAST. In this final preparation for mapping, we will first of all be turning this raster file into a data frame, and then we're going to be doing a bit of a data wrangling to prepare this raster for plotting. So we'll be working a bit with values, breaks, and also defining color palette and our general plot theme. As our first step, we'll be transforming our raster file into a data frame, and for that we will be using the as data frame from base R, and then passing here this REM final that we previously created, and then also saying here that we want the coordinates to be returned. If you here again inspect the first few rows of this data frame, you might be confused that you actually don't see here anymore the elevation column. Instead, you have this layer 1 and layer 2, and layer 2 has missing values. You can ignore this layer 2 column, which was used simply for the purpose of that model and the interpolation itself. What you actually have as elevation here is this column number 3, which is called layer 1. And actually now in this next step, what we'll be doing is simply renaming this layer 1, this third column, into simply elevation. So we can just simply write here, as we did before, we can use names base function, and then we're going to be changing only this one over here, and then again we can call this one elevation. One of the cool techniques to increase the variation in your elevation values is to actually use logarithmic transformation of your current values. So this is going to make sure that we have a bit more variation, and to do that what we can do is the following. So we can use this log1p for the logarithmic transformation, but the problem is that, as you know, elevation values can also be negative, or they can be also 0. So what we need to make sure here is that they do not actually, that we can also transform everything. So we need to kind of here normalize this value. So we can normalize them in the following way using this pmax function here. And then from our REM-df, we're going to be using elevation. And then we need to actually pass here some very, very small value that is going to make sure that we also log transform the negative values and the 0. So we can maybe call it here epsilon. and that this value can be super, super small. So it can be, for example, with 10 decimal places, so extremely small. And then we can pass this epsilon just over here, which is then going to help us achieve this. Now, to achieve this, we actually need to create a new column within this REM df. And what we can just simply do is we can pass it here, and we can, for example, call this one elevation log, so that we actually know what we are doing. Elevation log, and then pass it just over here. Another cool technique to make sure that we have good variation in our values is to define breaks. And for that, we can use natural breaks from the class int package. So I used this in so many previous tutorials that I lost any count, but I'm using it again because it's super, super useful. So I'm going to be using class intervals, so not classify intervals, but class intervals from the class int package. And then we actually, what we want to define here, what we want to define in terms of these breaks is this one that we previously created. So that would be this elevation log. And once this is done, we can then define, for example, we can go for 12. We're not going to be showing the legend, but this is just going to help us create these natural intervals. And then for the style, we can, for example, use Fisher style. And very important here that to get the breaks, because it's going to be list object, you need to also pass here this name. So what would be a relative elevation model without a very artsy palette? So we're going to be using here a macro palette, and I'm going to be showing you here what exactly I will be doing. I'm going to be a bit messing up with that palette and selecting a very extreme ends of that palette. So both the very light and very dark values, because I really want to accentuate that relative elevation model for our Snake River. Here's what we're going to do. First of all, we're going to be fetching this colors for this specific palette using HCL colors. You should check out HCL colors. They have really a lot of palettes, very cool ones, and you can use some other ones for this purpose. So I'm going to be using this macro palette over here. Then I'm going to be defining here the values. And then finally, I'm going to be reversing this. I'm reversing this because I want to make sure that the lighter values are associated exactly with our river surface, river elevation. And then the rest is darker values are associated with that elevation around our river stream. So that's the first thing. Then we can actually go ahead and inspect, you know, how these colors look like. And based on that, we can then choose what are the specific colors from this palette that we want to keep and use. So here's what we're going to do. We're going to, first of all, here say that we want to plot here the values, and we want to actually take the values from 1 to the maximum of these colors. And then for the colors, we're simply then going to pass this Mako palette for our colors. So this is the color palette that we just chose, but what I would like to do here, I want to hack it a bit. So I'm going to actually use this value number 1, so extremely light, and I'm going to use that for rivers. And for the rest, I'm going to be using from 8 to 12 inclusive to have a very sharp contrast here between the river elevation and the rest of the landscape. So here's how we can do that. Defining this PAL, and then from the calls, we will be taking only specific ones. So as we said, we want to take 1, and then we want to take from 8 to 12. So this is then going to make sure that we have a very nice high contrast. And what we can do is we can again make this pie chart, but instead of taking calls, we can simply here take PAL and see what we get. Okay, so going back to drawing board, this is exactly what we wanted. We wanted this extremely light value at the lower end, and then having immediately transitioning to something very dark and ending with almost a black color at the end of the spectrum. Last but not least in this map preparation is defining our ggplot2 theme. So I'm going to go ahead and define our legendary theme for the wind. which is first of all gonna have theme minimal. So it's gonna get rid of most of the stuff that we don't need. And then we're gonna go ahead and use this theme and define some elements. So some of the things we want to define here is that we don't want any access lines. So access line needs to be set to element blank. Apart from this, we also don't want to have any X titles here. So, sorry, not axis titles. So axis titles also needs to be blank. Now we're doing all of these things because if you have a bit older version of a rayshader later on, you might want to make sure that you actually turn off all these elements so they don't really appear in your render. So we also need to do this for the axis text. So I'm just kind of copying here and pasting. And then you need to do the same for the panel grid major. So it needs to be element black. And you need to do that also for the panel grid minor as well, just like this. Now, after this is done, what you need to do is, well, you don't need to do, but what I'm going to do is I'm going to turn off here the legends because we are being artsy here, right? So we're going to be turning off this legend. We're not going to be showing, we are just going to be admiring the art of relative elevation models. So once we do that, then we can also define some other things. So for example, our plot background, something that is going to be around, of course, our relative elevation model is not going to be blank. So this is actually rectangular fashion. So that's why I put in here element rect. But what I would like to do here is I want it to be filled with white. But in terms of the color of the borders, so this one, I'm just going to turn them off. So I'm just putting here color equals NA, but without, of course, this double quotation marks. And then once this is defined, you can also go ahead and define here your plot margins. So what I like to do is I like to decrease these plot margins as much as I can so that most of the space is actually filled with the map itself. So I'm going to go here and then define that for the top value, I want to set it to 0. So I don't want any space around the top side, but I'm going to do that also for the right hand side. And I'm going to do that for the left hand side. And I'm also going to do that for the bottom side of our plot. And for example, here we can put that it's in centimeters. It also accepts some other values, but essentially that is the main thing. Now, theme for the win. One thing that I did not define here at the beginning is that this actually needs to be a function. So this is something I actually forgot to do. So I need to define it here as a function. And then at the end here, I also need to close this one. So you need to make sure that you define this theme for the win as a function once more. We put all these elements here. And then at the end, you also close this one because we will be calling this theme for the win in the next step in our ggplot. Okay, and we can finally write now ggplot2 code. I'm just going to call this a REM plots. And then we start off, like always with ggplot, we need to call this ggplot function. And then within this ggplot, what we can do now, we can define, first of all, the data that we'll be using. So that's this one. And then within the main aesthetics, you need to define 3 things. First of all, what is going to be your X coordinates? Second, what is going to be your Y coordinates? And third, how are you going to fill those raster pixels? And we will be using this log version of this elevation. Now, for the second aesthetic, this needs to be a geom raster. So we are dealing here with that raster. And then finally over here, what we need to do is define what is going to be our palettes and what are going to be our breaks. So we did all of these things and we don't need to worry about that. So what we can do is just use scale field gradient, and we're using that one because we're using continuous values in this one. And then we can define. So first of all, our breaks are well defined. Second, our colors are defined in terms of that palette. And then finally here, we don't want to have any name. So I leave this open so that it doesn't give me the name of the legend. But anyways, we coerce the legend not to show up. And then over here, we can just add here this theme for the win. Behold, the delicate glowing threads of the Snake River's veins that cut through a moody, ethereal canvas of deep purples and soft blues, creating an enchanting interplay of contrast and texture. Guys, I really like how this turned out. Let me know in the comment section below what you think. And also, I'm wondering how this will look like if you use some other palette from HCL Colors. But this is not all. I also want to show you how you can build wonderful 3D plots based on this data that we have. And for that purpose, we'll be once again using rayshader. So let's go ahead and do that. First of all, I would like actually to define the width and the height of this one. So I want to actually really eliminate that white space that we had before. And for that, I would like actually to go ahead and take the measures here. So for the width, we essentially need the number of the columns from that raster file. And then for the heights, we can use number of rows also from this REM file. Now the thing is, this alone is quite actually big. So this width is 3.8K and this is 3.4. So essentially for creating the rendering the scene in rayshader, we don't need this. We don't need this big. So what we can go ahead, we can actually divide this by 500. Then we can get something which is in inches. The reason for that is we'll be using now plot.gg, and in plot.gg, width and height of the scene are defined in inches. Of course, you don't need to follow what I'm writing here. You can also select simply some generic numbers. It can be, for example, 500 by 500, 800 by 800, or anything else. But I'm using this simply to kind of minimize the white space around the plot and only render the scene where we can see this elevation. Once more, we'll be using here plot.gg. And now for our GG object, that's the first thing we need to pass. That would be that REM plot. This is what I really love about the plot.gg function. You can simply pass your previously created ggplot object, and then you can turn it into a beautiful 3D map. So for the width, we'll be passing here this object width that we created. So this would be, so we need to actually rerun again. But this width would be 7.72. I think that's pretty reasonable. Everything that is up to maybe 10 is really good for inches, and the height is going to be 6.83. So I think these are really good measures. Now, for the window size, we need to make sure that we take, because we have variable here, width and height, that we take the same for the window size. Now, for the window size, however, starting with width, this would be too small. So we actually need to scale back here a bit. I'm going to actually multiply it by 75. And you also need to multiply, unless you want this stretched, and I hope you don't want stretched, the window of this render scene, you want to multiply it by the same coefficient. So now if I do this, this is going to be 578. So window size is in pixels. 578 for pixels is totally fine. And 512 will be the height. Again, also fine. Again, if you're using here constants and not variables like I'm using, you can then go for something 6 by 600 or 8 by 800 or something else. Then for the scale will be how sharp our this elevation is going to be, how rugged is it going to be. 150 is something which is default, but I'm actually going to decrease this 2 times. So I'm going to decrease the ruggedness because I do want the river elevation model to stand out in this one. Now, except apart from this one, I like also to turn off this solid ground around the layer. So I just want to have the map. And I'm also going to turn off the shadows here. They're not really necessary because we're not going to have any background shadows. Remember, we're going to be limiting that space around our plots. So this is not necessary. So, but we do need to, for example, define here the shadow intensity equals 1. So the remaining shadows are not too sharp. Those that are actually reflection of the elevation itself on the object. And then we can also here define, how much we want to increase or decrease the angle. I'm going to use almost a normal angle here, so 87 degrees. And I'm not going to be tilting the scene. So I'm going to be using it the same one we had created in our 2D plot. And then for the zoom, it's always hit and miss. So I'm going to use for now, for example, 0.64. And then the last thing is I also want to utilize multi-core here. So I'm going to put it true. If you don't have multiple cores in your CPU, you can just skip this one. Before you hit that run button, two things that I forgot here. One thing is you want to add here C in front of these brackets because we're here talking about the list of two elements, width and height. And second, we didn't really define here height. So make sure that you also write here height and that you pass this object over here. This is the outlook of our render scene, but I would really like to shrink this white space around it. So we're going to go ahead and go back and readjust actually the zoom levels. And to readjust the zoom levels, we can simply use render camera from rayshader. And over here, we can simply choose a different zoom so we can actually decrease it a bit. For example, we can take 545 and then let's see what we got. Yep, this looks much better. So we don't have any more that white space. We got rid of it, but we kept essentially this plots in the bound. So I think we're ready to go write the scripts also for now rendering the object itself and saving it locally as an image file. And to render the objects as an image file, we can use our old good fellow, which is called render high quality. So render high quality is going to help us do that. Within render high quality, what we need to do is, first of all, define the file name. So for this one, we can, for example, call it 3D Snake River, and it needs to have an extension. So I'm going to go here for PNG. Then we also want to enable the preview as this scene gets rendered. Now for the lights, I'm actually going to turn off the rayshader lights, and I've been doing that for many times and in many previous tutorials because there are very cool environment lights that you can fetch from polyhaven.org. And then from polyhaven.org, we're going to be going for a specific image file, or actually light file, HDRI file, which is called Rosendale Plains 2. Okay, so we're going to be fetching the URL from this one, and then going back here to R, what we're going to do is we can go ahead then and download this one. So I'm going to just kind of a copy here, paste from that website, and then we can actually download this file. I'm just going to call it HDRI file, and I'm going to fetch the base name of this URL over here. And then we can go ahead and download this file. Of course, you can go ahead and manually download this to your folder. That's also fine. It's going to work. I'm just going to write here for people who are going to decide to simply do this in R. What is important is to also define here the destination file name and also to choose the binary mode. And then once you actually define this, you are good to go. The next step, what you will do here is define your environment light. So it needs to have a name like this, environment light. And then you need to call it here, of course, this HDRI file. Let me move this a bit. Then you need to choose, okay, what is going to be the intensity of this light? And for this one, it's a bit stronger. So I'm going to actually go for, let's say if one is a baseline, I'm going to make it a bit darker. It's a very strong light, as you will see. You can also choose here how your light is going to be positioned. So where the shadows are going to be. I'm going to keep it at 90 degrees. So shadows are going to appear at 90 degrees. They're fine with that. Then I'm also going to turn on here the parallel because I have multiple cores. And then I'm also going to define here the width as well as the height. Now for the width and height, you remember that we're working here with pixels, but our original width and height are essentially in inches. So we can actually put it back to the original value by just simply multiplying here by 500. Again, if you're not using here a variable for width and height, make sure that if you're using constants, the constants are in the same ratio like those that you use for your scene. So that's why I'm here multiplying both the width and the height with the same coefficient, which is 500. And then last but not least, I like to turn off the interactive feature of a rayshader. which allows you actually to move the scene, this object as it gets rendered, but this can actually crash your whole scene, and then you need to restart your session. I really like how this 3D plot turned out, and if I actually zoom it in a bit, you will also see here superbly intricate lines, but now in 3D, which gives off I think even a better experience than the 2D, maybe just a bit biased towards 3D maps. But yeah, essentially, this is how you can create also 3D plots based on your ggplot objects for this river elevation models. So this is how you can create some really powerful relative elevation model maps based on lidar data in a few easy steps in R using ggplot2 and a rayshader. Guys, I'm really excited for you and how you take this tutorial to some other river stream and create some awesome relative elevation maps. If, however, you would like to replicate today's analysis, I prepared the link to the GitHub repo in the description box below. So do check it out. Feel free to clone it, reuse it, modify it as you see fit. Let me know how it goes for you in the comment section below. And also, if you are new to R and you would like to expand your data visualization and geospatial knowledge in R, check out some of the few tutorials that I prepared for you. See you next time.